Right, now it's my pleasure to introduce our first speaker, Martin Siegert. Martin is the co-director of the Grantham Institute, and he's a glaciologist, I believe, by training. He's undertaken 3 visits to somewhere I've always wanted to go, which is Antarctica, and was awarded the Martha T. Muse Prize for Excellence in Antarctic Science a couple of years ago. So, Martin, over to you.
Thank you very much. So yes, my name is Martin, co-director of the Grantham Institute, and I'm a glaciologist. I study the ice sheets in Antarctica, Greenland as well, and it's quite exciting. I've helped fly aircraft into unknown bits of the ice sheet, drill holes, or tried to drill holes down into the bottom, and it's an exploration sort of thing. But it's undeniable that the Antarctic ice sheet and the Greenland ice sheet is experiencing change, and I want to talk to you about the science of climate change and what I understand as a glaciologist, but for some other things as well, because that's really the reason that we are here. So this hopefully won't be news to you that we are living in a world which is warming, and we have records going back several decades now, and although there's some complexity in the signal, at the moment the planet is warming. It's undeniable. Excuse me. So this is something that we need to take some notice of. The last few decades experiencing extreme levels of warming, and the question is what is causing that? And it's pretty straightforward to understand, is that warming is associated with increase in the concentration of atmospheric greenhouse gases. So this is 3 slides, 3 depictions of the atmospheric carbon dioxide, which is greenhouse gas concentration, on a variety of scales. And we've got a pretty good way of being able to measure the level of carbon dioxide in the atmosphere at a variety of scales. On the top left is the last few years, and you can see there's a fluctuation in the amount of carbon dioxide. That's from the Mauna Loa Observatory in Hawaii, and that's simply because of the changes in the biosphere in the Northern Hemisphere interannually, so that's easy to understand. Going back several decades, the bottom left, you can see there's a steady increase in the amount of carbon dioxide in the atmosphere going back 1960, and we are increasing. In fact, now we have topped over 400 parts per mil. So that's a milestone, if you like, a wanted milestone, but nonetheless we have done it. Historically, you can go back even further and say that over the last 1,000 or so years, in the middle panel, carbon dioxide has been pretty level until the Industrial Revolution. And so if you need a trigger for why carbon dioxide in the atmosphere started to go up, it was as a consequence of industrialization, and in other words, we're responsible for it. And again, you can go into Antarctica, the Taylor Ice Core at the bottom, gives you an even longer time frame. You can look in the geological record as well, going back hundreds of thousands and millions of years, and you can see there is natural variability of these things, and often climate skeptics misuse that type of information to say, oh, don't worry, it's just natural variability. What we're seeing in the middle panel, this is the classic hockey stick relationship, is that it is really undeniable that carbon dioxide concentrations of greenhouse gas started at the Industrial Revolution to go up in the way that we're seeing it, as did global warming. So this is something that we think is a coupled system, and we need to address it. If you want confirmation of that, there's lots of modeling studies that have been done. So on the left panel is the black line is the measurement of global temperature, and we can run an atmospheric ocean coupled model to determine what the amount of warming in the future and in the past, of course, might be like. So we can train these models with past data. And if we don't account for carbon dioxide concentrations and all the associated processes, then we're not able to match the measured record of greenhouse gas changes. But if we do put those things in the model, actually on the right-hand side, you see we get a very nice relationship. So our intuition about the coupling between atmospheric concentrations of greenhouse gases and global warming is pretty well matched with physically based models of the system that we, as best we can. There's been a lot of debate about the hiatus the last 10 or so years. Global warming has been going up for several decades, and we're in a hiatus. And again, you might hear climate skeptics say, oh, don't worry, it's all leveled off. There's nothing to worry about. Well, actually, there's been quite a lot of debate in the scientific literature about whether the hiatus is real or not. But notwithstanding that debate, last year was the warmest year on record by some way. And of course, the first few months of this year are even warmer than the comparable months in the previous year. So if there was a hiatus, which is an open debate, it's probably gone. So we are back on the upward trend. So that's interesting. But atmospheric global warming levels, that's not the only data set that we should bear in mind. There are several independent data sets that point in a similarly difficult position. We can look at the Northern Hemisphere spring snow cover, and you can see there's a downward trend. It's been reduced in time over the last few decades. We can look at the level of heat in the upper levels of the ocean, and that is going up because the oceans are absorbing heat. We can look at the Arctic sea ice extent, and that's covered a lot in the media and in the papers. That is going down, and we can look at global sea level, and that is going up. And it's going up as a consequence of the oceans expanding thermally because they're taking up more heat, and it's going up as a consequence of the ice on our planet above the level of the ocean melting and decanting that water into the sea and pushing sea levels up. Now, of course, we've got a good idea about temperature and how it's changing on the planet, and it's not a uniform thing. The level of global warming that is taking place is regionally specific. There is so coherence to things, but generally there are some hotspots and there are some places where global warming might not be so bad. I was just saying the Arctic and then the Antarctic, these are some of the regions, it's not shown in this map, where you get the greatest level of global warming and some of the most obvious reactions to those things. So what do we do about it? And this is why we're here today, because the science has been described on several occasions by the Intergovernmental Panel on Climate Change. We do a lot of work into the IPCC. Professor Jim Skee, who is an Imperial College scientist, is the co-chair of one of the working groups, Working Group 3 of the next IPCC. He's been involved in several of them. And it's through the IPCC they were able to have such certainty about global warming and the anthropogenic influence on that. And so the question then is, well, if it's our fault, then clearly maybe there's something that we can do about it. And of course, this is quite a complicated form, but on the left-hand side, this is a description of various energy mixes that you can have to fuel the energy requirement on our planet. And these RCP numbers are from the IPCC, sorry about all these anagrams, the IPCC document, which tells you about different types of scenarios. And what to remember is the 2 degrees is often talked about from Paris and in the IPCC documents as the level above which global warming becomes, in inverted commas, dangerous. And so we want to keep global warming to within 2 degrees. We've already got to 1 degree, by the way. RCP 2.6 gives us that. It keeps global warming to about 2 degrees. RCP 8.5 is carry on as normal. It doesn't exist. Don't worry about it. And you can see in each of these scenarios, in the middle panel, there are different carbon dioxide emissions that come out from that. The green one, RCP 2.6, means we basically decarbonize our system by the second half of this century, which is what people are talking about doing now. RCP 8.5 takes us to unknown territory. The level of carbon dioxide concentrations now, 400 ppm, is way outside the natural envelope of things. When you look at the Vostok ice core, carbon dioxide concentrations do vary naturally between glacial cycles and interglacial cycles, but they never, in interglacials where we are now, they never get to 400 ppm. You've got to go back to 3.5 million years ago in the Pliocene, where sea levels were several meters higher than they are, and the vegetation mix on our planet was completely different. So if we do nothing, we've sort of set the thermostat on our oven to a very high temperature, and if we do nothing, we'll get there eventually. And so that's something that's going to be difficult for us. All this is really saying is that we have some options, and there are some things that we can do about it. And this is where we are right now. Just started this part of the century. You know, we could go for RCP 2.8, and if we do that, don't worry about it. We'll get to a situation by the end of the century where the global temperature is 4 degrees centigrade. That is, actually, you've got to go back past the Pliocene for those sort of temperatures. But if we do something, then we can possibly keep the global warming to within that 2-degree threshold. But we have to do something. And this is an important diagram here, because carbon dioxide is a greenhouse gas. It's actually not the most potent greenhouse gas, but the problem is it sticks in the atmosphere. So if you put it up in the atmosphere, it hangs around for quite a long time. And what this really tells us, the bottom left panel describes that quite nicely, again, with the different mixes of carbon dioxide emissions. If we take RCP 2.6, i.e. do something right now, then the level of carbon dioxide can be pushed back down over some centuries. This is going up to 3,000 years, the year 3000. So it's talking about several centuries. If we do nothing, then the level of carbon dioxide hangs around for a long time, and we end up not just with our children having a problem, but many centuries of problems into the future. So these are issues which are ours to solve. They weren't necessarily ours created, because there's several generations before us, but nonetheless, we are the first generation that understands the situation that we have to do something to it. Our legacy, whether that's positive or negative, will be felt undeniably in the next coming decades and centuries. And of course, I'm a glaciologist, so I'm interested in how the ice sheets respond to all of this, and sea level is going up. There's no glaciologist that you'll be able to find that if you ask them, what's the sea level going to be like in 100 years' time, none of them will say it's going to be lower. Right? Sea level is going up, and there's no doubt about that. And in fact, a lot of it is built in. There's such a lag in the system that sea level is going to go up regardless of what we do. And so the minimum it will probably go up is a few tens of centimetres, but if we do nothing, then it can reach over a metre. In fact, there was a paper that came out just a week or two ago by a colleague of mine, Rob DeConto, University of Massachusetts, who predicted that a lot of the models that we use in glaciology are not accounting for a particular process. And if you do put that process in, then the rate of ice loss is much greater than we've been accounting for, and he's predicting possible disintegration of the whole of the West Antarctic ice sheet within about 150 years or so, with global sea level going up by 3.5 metres. Now these are major, profound situations. There's so much ice on our planet, in fact, that if you melted the whole of Greenland and Antarctica, sea level go up by over 60 metres, and this is what the UK would look like if you do that. Okay, that's rather sort of scaring, but you don't have to. Yeah, where were you? You can pick your house and work out where you are with all of that. It's a scary thought. I mean, it's a situation on our planet. We have enough ice above the level of the sea that causes sea level to go up in that way. But of course, you don't need 60 metres to cause a major problem. A metre of sea level rise in the United Kingdom gives us serious coastal issues in Northwest Europe. So this is something to think about. And it's not just sea level is going up, the rate of change is also going up of sea level. So it started off relatively slowly. We thank the British Navy for this. The British Navy went around the world, sort of global policing of the early markets in the 19th century, and had tide gauges everywhere. And so we're able to have some idea about the rate of change of sea level going back to the middle part of the 19th century. And you can see, we're better measuring it now from satellites, the rate of change is going up. You often hear about extreme weather and things are getting warmer. Well, there's some things to think about here. The top graph is basically the whole thing is getting warmer. We're just experiencing more warm weather. And if you do that, of course, we'll have more hot days. But you also think about more extreme events, more cold, more warmth. If you couple those things together, then actually what you get on the lower diagram is the worst of both worlds in terms of it getting warmer. It generally is warmer, and you get many more extreme hot days. And so this is something we need to think about. So you often hear about the trillion tons of carbon. That's what we've got left. A trillion tons of carbon equates to 2 degrees centigrade, roughly thereabouts. And this is an interesting diagram, and it explains the various future scenarios that we might have. The black line is where we are right now. So we've basically burned half of it. That's where we are. If we do nothing, the red one tells us where we get to by the end of the century, way outside the trillion tons of carbon. And there's a variety of ones inside there, but they all exceed that, apart from RCP 2.6. And so we have options. We have various things to discuss today. It's important that we do that. Science has got us where we are, right? It tells us that there's a problem. It allows us to understand the processes that are taking place, and it allows us to understand that we're responsible for it. But science, unfortunately, it doesn't have the solutions. The solutions lie with governments. Policy is important. It relies on local action. People are important. They need to take responsibility. It relies in cities, because authorities are important. And in particular, it lies with business. And this is, I believe, I'm not a business person, I'm a glaciologist, but this is a very important thing for us to consider, how the business community understands the challenge that it needs to face. And this is hopefully the subject that we'll encounter today. It's lovely to be the first speaker, and thank you very much for your attention, and look forward to having lots of discussions with you later today. Thank you very much.
Thank